Hello, and welcome again to FlippedHarber for Precalculus. In this video, we're going to take a look at Section 1.3, Setting Up Equations, Applications. Our objectives for this video are to learn how to translate verbal descriptions into mathematical expressions. We're going to set up applied problems, and specifically we're going to solve interest problems, mixture problems, uniform motion problems, and we'll look at some constant rate job problems. Our outline for this video is to solve an interest problem, solve a mixture problem, a uniform motion problem, a constant rate job problem, and we'll look at a volume example. Finally, we'll take a look at what the homework is for this section. Taking a look at a basic interest problem. Betsy, a recent retiree, requires $6,000 per year in extra income. She has $50,000 to invest and can invest in B-rated bonds paying 15% per year or in a CD paying 7% per year. How much should she invest in each to realize the $6,000 in interest per year? Now I know it would be easier just to invest everything in the B-rated bonds since they do pay the highest percentage, but B-rated bonds aren't as secure as CDs are, so she doesn't want to invest all of her money into the B-rated bonds. She might lose it. So we need to pick out the important information in this problem. The $6,000 is what she's going to need to get out of interest. The $50,000 is her principal for the investment, and she has two rates, 15% per year and 7% per year. All of this is going to get plugged into the basic interest equation. I, interest, equals PRT, principal times rate times time. So again, her interest is the $6,000 she needs every year. The principal, that is the money that she's going to invest, is the $50,000. Now that's going to be broken up into bonds and CDs. So I set that $50,000 equal to B plus C. B for bonds, C for CDs. And I solved for B. Now whether I solve for B or C really doesn't matter. Our two interest rates, 15% for the bonds, 7% for the interest rate on the CDs, needs to be plugged in appropriately. So we take our basic interest equation, I equals PRT, and we split it up into two PRTs added together, one for the bonds and one for the CDs. So our $6,000 gets plugged in for interest. Our $50,000 minus C gets plugged in for one of the principals. We make sure that we use the appropriate rate for that. That $50,000 minus C is how much she's going to invest into the bonds. So I make sure I use the bond percentage rate. And then C is multiplied by the 0.07 for the 7% for the CDs. The 1 is plugged in because it's 1 year for both investments. She needs to earn that $6,000 in 1 year. So now we have an equation with only one unknown, and we need to start solving for that unknown C. So we start to distribute, and we combine some like terms, and we get negative 1500 equals negative 0.08 C. Now obviously you can just go ahead and drop the negative, but it'll disappear when I go ahead and divide by the negative 0.80 anyway. So we find out that Betsy needs to invest $18,750 in the CDs and $31,250 in the bonds. Again, the bonds are a riskier investment, so she's not putting everything into the bonds. She's kind of safeguarding some of her money by investing in the CDs. I've circled my answers just like they should appear in your homework. Since we have two answers, you want to box them together. Alright, let's move on to our next problem, a mixture problem. How many ounces of pure water should be added to 20 ounces of a 40% solution of muriatic acid to obtain a 30% solution of muriatic acid? Again, the 20 ounces, the 40% and the 30%, we're going to plug into our basic mixture problem, which is we take an amount, a volume, multiplied by a concentration, plus another amount times a concentration, and we set that equal to our total amount times our final concentration. So you need to be really careful what gets plugged in where. So the amount that we're trying to find, we use the variable x. Now the concentration for that, it's pure water. It's 0% muriatic acid. So I actually put in a 0 for that. That whole first term goes away. We're mixing it with 20 ounces of a 40% solution. So our amount is 20 ounces and our concentration is 0.40. Now we don't actually know our total amount, but it's going to be whatever we have of pure water plus whatever we have of the 40% solution. So I use the expression x plus 20 as my total amount, and that total amount needs to have a concentration of 30%, so 0.30. So now we're just going to solve this equation for x. Like I said, that whole first term goes away. X times 0 is 0. 20 times 0.40 gives me the 8, and I distribute the 0.30 into the expression x plus 20. Move the 6 over and divide by the 0.30. We find out that we need 6.67 ounces of pure water to mix with that 40% muriatic acid. My answer is boxed in just like it should be on your homework. Let's take a look at a uniform motion problem. These things are great. We see these on tests all the time. We see them on tests like the ACT a lot also. A motorboat can maintain a constant speed of 16 miles per hour relative to the water. So if the water's not moving, the boat can go at 16 miles per hour. If we're talking about flowing water, that flow can either speed us up or slow us down depending on which way we're going with the water. The boat makes a trip upstream to a certain point in 20 minutes. The return trip takes 15 minutes. What is the speed of the current? So we're trying to figure out how fast is the water flowing. So our important numbers are the 16 miles per hour and the two times, 20 minutes and 15 minutes. I've organized what we know and what we don't know into a table here. One thing that's the same is that the boat goes the same distance upstream and downstream. So I've made that just a plain D. Our speed upstream is 16 minus W, 16 miles per hour minus the speed of the current, because when going upstream, the river slows us down. When we're going downstream, that is with the flow of water, that speed of the current helps us. So the speed is 16 plus W. The time upstream is 20 minutes, the time downstream is only 15. So if we take a look at our speed equation, speed is equal to distance divided by time, but we're actually going to take that equation and solve it for distance. Distance equals speed times time. And that's actually the equation we're going to use because the two distances are the same. So since our two distances are the same, we use distance equals speed times time. But what we do is we take a speed times time upstream and set it equal to a speed times time downstream. Again, the distances are the same. So 16 minus W is our speed upstream times 20, our time upstream, and set that equal to 16 plus W, our speed downstream, times 15, our time downstream. So again, we've got an equation with an unknown to solve for. We distribute through the 20 and distribute through the 15. Combine like terms on the same side of the equation, so we move the 240 over to the left side, we move the 20W over to the right side, and now we just have to divide by the 35. So W, the speed of the current, is equal to 2.29 miles per hour. Let's take a look at a constant rate job. Again, these are great problems for the MME, the ACT, and the other tests that you have to take. Patrice, by himself, can paint 4 rooms in 10 hours. If he hires April to help, they can do the same job together in 6 hours. If he lets April work alone, how long will it take her to paint 4 rooms? So our equation for this type of problem is that we take our two individual rates, Patrice's rate plus April's rate, is equal to their combined rate. Now what we're talking about is the job that they can complete in a certain amount of time. This problem is set up with times to paint 4 rooms. So our job for the top of each of these fractions is actually the exact same thing. It's the times that will be different. So our job, no matter if we're talking about April, Patrice, or together, is 4 rooms. It takes Patrice 10 hours to complete that, so we put that as his time. We're trying to solve for April's time, so we put a variable t there. And we know that working together they can paint those 4 rooms in 6 hours. So that's their time together. Now I can go ahead and just replace 4 rooms with the number 4. It just represents how many rooms they can paint in that amount of time. But really, it's easier if we just realize that since they're all the same job, we can just make it 1. So when I get done solving for t, that's going to be the time that it takes for April to get the one job done. That one job is painting 4 rooms. So when I solve for that t in that equation, I'll be all done. Now how are we going to solve for this? You might be sitting there freaking out because this has fractions. If fractions bother you, the best thing to do is get rid of them. So how are we going to get rid of these fractions? Well, we're actually going to multiply by a common denominator. Now one easy common denominator would just be to multiply all 3 together. 10 times t times 6. That's a great common denominator. But instead I'm going to multiply by the least common denominator. I'm going to multiply every single fraction here by 30t. 30 is a good number because 10 is a factor of 30 and 6 is a factor of 30. So when I multiply the first fraction by 30t, I get 3t. When I multiply the second fraction by 30t, I just get 30. And when I multiply the other side by 30t, it simplifies down to 5t. So I've gotten rid of all of my fractions, which are a major sticking point. Yes, I've got t showing up in a couple spots in my equation instead of 1, but at least I don't have any fractions. So now I'll move that 3t over, and I've got 30 equals 2t. Divide by the 2, and I find out that t equals 15 hours. Now again, this is the time that it would take April to do one job, which is paint 4 rooms. So this is the time that it takes April to paint 4 rooms. Let's take a look at a volume example. An open top box is to be made from a square sheet of metal by cutting a square with a side 1 foot from each corner and turning up the edges. If the box is to be 4 cubic feet, what should be the dimensions of the sheet metal? So we need to stop and think about this. An open top box, you can think of it as a shoebox without the lid. Okay, we don't have to close in the box totally. We just have to make the 4 sides and the bottom. So we're going to take a square of sheet metal, and I've got that square of sheet metal labeled X because that's what we're asking. What should be the dimensions of the sheet metal? If I cut 1 foot from each corner, I get this kind of shape. So my side becomes X minus 2 because we took 1 foot above and 1 foot below. So now our volume equation is length times width times height. Well, what's our length, what's our width, and what's our height? Well, our length and our width are both X minus 2. Those flaps are going to be folded up, and the bottom of the box will be X minus 2 wide, X minus 2 long. The height for the box is the amount that was cut away. It'll be 1 foot tall. So I plug in 1 for our height. Now what I end up with when I multiply together on the right side is a quadratic. Now I'm going to go ahead and move the 4 from the left side over to the right side, and it's going to cancel that plus 4 that's on the right side. So I'm going to get x squared minus 4x, and that's now equal to 0. Now since this is a quadratic, we've got a lot of different ways to solve it. The best way, the first way that you should try to solve a quadratic is always by factoring. And this one can actually be factored pretty easily. Just pull out an x. So you have x times x minus 4 equals 0. We set each of those factors equal to 0 and we solve. So we've got x equals 0 or x minus 4 equals 0. This first one's already solved. All I need to do is add 4 to the other side. So my two solutions are x equals 0 or x equals 4. Now I can only use one of these. Because x is representing the size of a piece of metal, we can't really talk about making a box from a sheet of metal that is 0 feet by 0 feet. So we'll throw that answer out. The one that we box in, the one that we keep, is x equals 4 feet. So the original piece of sheet metal should be 4 feet wide and 4 feet long. And that will make us a box. Once we cut out the corners and fold it up, that box will be able to hold 4 cubic feet. So that's our last example. You should already know what the homework is, but here it is again. Hope you took good notes. If not, you might want to back up and write those notes down. You need to remember to always take notes during the video, because I'm going to pull questions from these videos to include on your binder tests, binder quizzes. So make sure you're taking good notes, because you get to use those notes on those binder quizzes. So hope you enjoyed it. I'll see you in class, and I'll see you online.